At the end of the last video, we had talked about the four basic properties of gases: pressure, temperature, volume, and quantity or number of moles. Starting out in the late 1600s, chemists began to study the relationships between these different properties, and they came up with a series of gas laws. These were basically mathematical formulas that allowed us to relate various of these four properties. The first one to come along in the late 1600s was Boyles Law. Robert Boyle was considered the father of modern chemistry. He was the first person to really begin to quantify chemistry. And Boyle studied the relationship between pressure and volume. Now, if you think about pressure and volume, how are they related? There's always two possibilities, either inversely or directly. If two properties are directly proportional, then they change in the same direction. So if the pressure went up, the volume would go up. If properties are related indirectly or inversely, then they change in opposite directions. So an increase in pressure would mean a decrease in volume. Now, if you've ever driven up to the mountains, maybe to have a picnic on a nice summer day, and you've got some potato chips with you, you may notice that at that high elevation, you open up the sack and the potato chip bag has expanded dramatically. Okay, this is what happens when you drive up to 9,000 feet in elevation. That would be just like Carson Pass up on Highway 88. So as we went up into the mountains, the pressure decreased. The higher you go in elevation, the lower the pressure is, and it appears that the volume of the potato chip sack has actually increased. So a decrease in pressure seems to have led to an increase in the volume. So that would tell us that pressure and volume are inversely proportional. So Boyle came up with a mathematical equation to relate those, where P1 and V1 would have been, say, the pressure and volume of the potato chip bag to start with, and P2 and V2 would be the final pressure and volume once they got to the mountains. So like any algebra equation, if you know any three of these, you can solve for the missing value. So let's suppose that we started out here at sea level in Stockton with a pressure of 1 atmosphere, and there was 1 liter of air inside the potato chip bag. Now, if we increase the pressure, say we went somewhere where the pressure was greater and the pressure doubled to 2 atmospheres. Well, if the properties are inversely proportional, then an increase in the pressure should result in a decrease in the volume. And what Boyle discovered was not only is it inversely proportional, but it's quantitative. So if we make the pressure 2 times greater, the volume should be 2 times smaller, or half of its original value. So the volume would change from 1 liter to 0.5 liters. So 1 times 1 gives us 1 on the left side, 2 times a half gives us 1 on the right. So whatever change occurs in pressure, he discovered that the opposite change would occur in the volume, and that's Boyle's Law. The second of our 4 major gas laws is called Gay-Lussac's law. And Gay-Lussac looked at the relationship between pressure and temperature. So pressure and temperature, again, would have to be either inversely proportional or directly proportional. Now, if you've ever read a warning on, say, a can of shaving cream or hairspray, it always says, keep away from heat. You don't want the temperature to go too high, because if the temperature gets too high, the can might explode, which suggests to us that as the temperature increases, the pressure must be increasing as well. And that makes sense, because if we increase the temperature, then the molecules of gas are going to move faster, they're going to hit the inside of the can harder, and they're going to create more pressure. So heat plus an aerosol can, never a good idea. At the end of this section, I'll show you a little YouTube video where someone did this. It's not the kind of thing you want to do at home, but it's pretty fun to watch. So Gay-Lussac discovered that pressure and temperature were directly proportional. As one increased, the other increased, and vice versa. And so he came up with a second gas law where P1 and T1 are our initial pressure and temperatures. That would be the temperature of the can to start with and its temperature. And then P2 and T2 would be the second or final pressure and temperature. So because it's in the form of a fraction, if one of them increases, the other one must increase by the same amount to keep the fraction equal. So, for example, if the pressure initially were 2 atmospheres inside the can and we were at 300 Kelvin, and let me remind you, of course, that the temperatures have to be in Kelvin. Whenever you're doing gas law calculations, we always have to use the Kelvin temperature, not Celsius or Fahrenheit. If we increase the temperature to 900 Kelvin, we've basically tripled the temperature. Well, if the temperature tripled, then the pressure should triple as well, and it will now become 6 atmospheres. So that's Gay-Lussac's law. Don't try this at home, guys, but this is what happens when you increase the temperature of a gas in a sealed container. The third gas law we're going to discuss today is Charles' law. Charles looked at the relationship between volume and temperature. So again, volume and temperature must either be inversely or directly proportional. So for an example, let's take a look at a balloon here. So we have a regular balloon at room temperature, and then we have a second balloon where we pour liquid nitrogen on it, and the liquid nitrogen makes the balloon very cold, and you can see that the volume is decreasing. So it appears that volume and temperature are directly proportional. As the temperature decreased from the cold liquid nitrogen, the size of the balloon decreased as well. So Charles came up with an equation that's similar to Gay-Lussac's law. Because volume and temperature are directly proportional, it's in the form of a fraction. So V1 and T1 would be the volume and temperature of the balloon to start with, and V2 and T2 would be the volume and temperature at the end. So, since they're directly proportional, whatever happens with one of these should happen to the other. So, for example, if we started out with a balloon that contained 120 milliliters of gas at a temperature of 300 Kelvin, if we decrease the temperature by adding liquid nitrogen, so we've essentially cut the temperature to 1/3 of its original value, so we would expect the volume to decrease to 1/3 of its original value as well, and it would now become 40 milliliters. So that is Charles' law. The last of our 4 major gas laws is Avogadro's law. Now, the one variable we haven't really talked about yet is moles, and of course Avogadro is famous for his number, which is the number of items in a mole. So Avogadro's law looks at the relationship between volume and moles. And again, the 2 variables are going to have to be either inversely or directly proportional. This first balloon, not being inflated yet, has only a little bit of air in it, so there's only a very small amount of moles, and the volume is small. If we add a lot of air to the balloon, it becomes much larger. So by increasing the number of moles of air in the balloon, we've increased the volume. So it appears that volume and moles are directly proportional. And that makes a lot of sense. It's pretty obvious that the more air you put into a container, the bigger the container ought to be. So Avogadro's law, since the 2 variables are directly proportional, looks a lot like Charles' law and Gay-Lussac's law. It's in the form of a fraction. So any change that occurs in volume, a comparable change would have to occur in the number of moles so that that fraction would remain the same. So for example, if we started out with half a mole of air in a balloon and it had a volume of 11.5 liters, if we increased the number of moles from 0.5 to 5, that's a 10-fold increase in the moles. We would expect a 10-fold increase in the volume, and now the volume would be 115 liters. So again, any change that occurs in the moles, a comparable change will occur in the volume, and that is Avogadro's law.